Hello everyone, this is Tom Hutchings from RBR. For our next session at BankSec 2020, we're joined by not just one, but two expert speakers. We're going to be exploring the role of the Trusted Platform Module, or TPM, in ATM security. First joining us is Aravinda Korala. Aravinda is the CEO of industry software specialist CAL. Also with us is Ian Robertson. Ian is a Senior Vice President with NCC Group, looking after the group's Canadian business. Aravinda and Ian, welcome to BankSec 2020.
Thank you, Tom.
Thank you very much.
And Aravinda, over to you.
Thank you, Tom. So TPMs and security. This talk is a little bit about why TPMs are very important for ATM security and the fact that TPMs are not properly used in most bank environments, and this is an attempt to try to change that. Let me tell you a little bit about TPMs and where we are going with TPMs and this conversation about the importance of TPMs for locking down ATMs. Now, firstly, ATMs are, of course, not just about cash dispensing, in the sense that obviously there's a lot of money inside the ATM, and the ATMs need to be looked after. There is a risk of the cash being stolen from the ATM. Everybody understands that. But of course, it's not just about the cash inside the ATM, because the ATM is the gateway to all of that back-end technology that a bank has, core banking, the ATM host, all of that. And that gateway allows cash, not just cash to be dispensed, but for funds to be moved around, for funds to be transferred. So the risk if an ATM is attacked is not just limited to the cash inside the ATM, but the risk is also, what transactions could be authorized using that ATM, moving money around, all of that. So clearly, no doubt whatsoever that ATMs need to be locked down really well. Now, having said that, it is a little bit of a surprise that ATMs aren't really necessarily locked down as well as they can be. And even more surprising is that a component called the TPM, which is built into all PCs and most ATMs, isn't properly used even today when locking down ATM networks. So here, the way to see a TPM is that it is a little chip on the motherboard that is standard on every PC. In fact, today you can't buy a PC that does not have a TPM on board. Pretty much every PC system, every laptop, every piece of hardware that is PC-based that a bank might have has a TPM on board. There's a lot more detail about this in CAL's white paper, so we would encourage you to have a little look at that. This is a quick summary of what we cover in that white paper, which was published in August. Now, what exactly is a TPM? So a TPM is primarily, firstly, a secure hardware vault for storing keys. And keys are important because all security depends on some form of encryption and a key that is required for that encryption algorithm to work. Now, of course, those keys need to be secured, need to be stored very carefully, and it can't be stored in software on a hard disk. There is just no way that you can store keys securely just on the hard disk by itself. It needs to be, if you encrypt the key, then there's another key that is needed in order to decrypt that. At the end of the chain of keys that you might use, there is always a clear key, and that clear key needs to be stored somewhere securely. The TPM is that place on a PC. Now, the TPM is not just about storing those keys, because let's say that you have a nice secure place to store that key. Then the question is, whom do you give access to that key? How do you know that whoever is asking for the key, the piece of software that's asking for the key, is secure? Well, the TPM has a very interesting concept called core root of trust measurement. In other words, what it does is to make a determination as to whether the software inside the PC is trusted, and it does that by checking to see whether the software has changed from a gold scenario where you explain to the TPM, what that software is, and you make sure that that software hasn't changed. And if that software hasn't changed, then it is okay to hand over the key. So there is a process that is called secure boot, and there are other little details like platform configuration registers called PCRs that allow the TPM to help with securing that startup process. Once Windows has booted, and especially what is on the hard disk needs to be encrypted, and that encryption is normally done using Windows BitLocker, and BitLocker stores its keys using the TPM. And that's, again, super important, because where the keys are stored tells you how secure that storage is. If it is held on the hard disk in the clear, then obviously it is not very secure. If you think about the process of booting up, like, you've heard of blockchains, it's a little bit like a blockchain where there are blocks of software where you check that each of those blocks hasn't changed. And the TPM is something a little bit like a blockchain that allows each of the steps in the boot sequence to be checked to make sure that nothing has been modified maliciously. And in fact, this can be carried on not just for the boot up part of Windows, but also for all the software that runs inside the application environment. Now, a little bit of detail on how the TPM works. There's a fabulous book. This is the book. It is free to download, called The Practical Guide to TPMs. And there's lots of detail there that the security department of every bank should use as its Bible when deciding how to secure ATM networks. And one of the things in that book, and I've just listed some of the use cases, please take a look, please cast a quick eye over them. You will see that it's not just about securing the boot up sequence, it's also about everything that the bank might do in an ATM environment. It's about VPN security, it's about password security, and so on. And all of that should be rooted in a hardware secure element, which is the TPM. Now, the purpose of this presentation is partly to make banks sit back and think whether their network is really, truly, properly secured. It's not just the ATM that needs to be secured in this way. And you will see that I have put a little green blob in each of this network of systems that take part in an ATM transaction. So for example, there are the ATMs at the bottom, there's an ATM host in the middle, there are HSMs, there are web services, there's a switch there, there's core banking. And of course, the ideal scenario is that each one of those things has a hardware secure element, which would normally be a TPM, but in the case of an HSM, it will be the HSM itself that is able to firstly store keys in a secure way, but secondly, is able to measure the integrity of that system so that when, for example, a connection is set up between the ATM and the terminal handler, then both systems verify that the two sides have been secured and the platform on which they run does not have any malware before that connection is carried out. An absolutely vital way of ensuring that the complete network is totally secure. Now, to tell you the truth, most banks are not at this stage yet. They should be. And of course, what else is there more important than securing your ATM network that can not just dispense cash, but move cash and funds around the world. This slide here is about how that technology can be moved into protecting some of the assets inside the ATM itself. For example, the cash dispenser. Many of you would have heard of black box attacks and so on. So this concept should be used for protecting against black box attacks as well. And one of the things that has happened recently is that the XFS committee has picked up this idea and is running with what is called end-to-end security, that is between the cash dispenser and an external host. So this is being built into the version 4 of the XFS standard. that will be made available in preview form at the end of this year, and then there'll be updates to that next year as well. So the good news is that the XFS committee has picked up the idea that TPMs and hardware secure elements are really, really important, and it will allow ATMs to be locked down much better than they have been in the past. More detail about TPMs and the CAL white paper from our website, www.cal.com. Thank you.
Good afternoon. I'm Ian Robertson, and following on to Aravinda's presentation, this is just a bit of background on what a TPM is, what it isn't, and a little more about, in the abstract, how it secures systems and networks. So just jumping right in. A TPM is a hardware, was originally a hardware security module, but not an HSM, but a crypto coprocessor, traditionally an external chip. We've got an example here on the side of the screen. More recently, it's been implemented inside trusted execution environments, for instance, inside in AMD or Intel chips. So the good news is, well, before you had to either specify a system with or add a daughter board. Now it's coming free with CPUs. Applications, common, numerous. You find it in just about every server or laptop. It's very common in IoT devices. We can also see it in ATMs, hopefully. And it enables low friction security experiences. So from a user standpoint, this is about adding security without a lot of cognitive load or other requirements. It enables things on your PC like Windows Hello, which is logging in via biometrics, in that case, visual biometrics, BitLocker, securing and encrypting the data on your hard drives, UEFI Secure Boot, which we had touched on, and WDAC, which is a whitelisting of applications. So checking to see if an application is allowed on a whitelist before it's, I guess, permitted to execute. Moving on to the functions and internals of a TPM, we see here on the side a legacy TPM, which would be used to enable this functionality on a system that did not have a modern processor or an onboard TPM. These are becoming pretty rare these days, but it's useful for us to consider that the TPM itself in the software operating environment stands beside the actual execution flow. There's a command response protocol which exists, and software interacts with this. So querying the TPM code or hardware itself and getting responses, whether that's exposing a PCR or releasing a secret or performing a cryptographic operation on behalf of that software. The TPM itself does implement a number of cryptographic primitives within it. So this would, again, be outside of the somewhat malleable software environment. It implements a random number generator, key generation. It contains code for hashing and HMAX and some elementary or very common cryptographic algorithms, including RSA. The TPM stores your security parameters. This is probably one of the first things that people think about with these. So those are your certificates, keys, or seeds. It stores them in a hardware level, and they're protected. There's access restriction to these sensitive security parameters, again, certificates, keys, seeds, and so on. It enables integrity checks through chains of hashes. So these are those PCRs that we talked about, and Aravinda likened to blockchain. Again, actually a pretty good analogy. I've got a quick little, I guess, formula for how these work. So each time that a measurement is taken, it's hashed with the previous state of the register and the argument or measurement that was taken. So in that way, it's cryptographically secured in a chain so that each step that was verified is also used to tie to and expose the or represent the system state at a point of measurement. There's not a single PCR, there are multiple PCRs, so we can measure integrity on various parameter chains, which means that we can choose what things are being used to unlock or verify different elements of system state. That's really useful because from an engineering standpoint, it also allows us to debug where a check failed and therefore what may have been modified in a system. Trusted computing applications, these are the three ones that we see. And here, modern implementations of TPMs, FTPMs, which you would see on contemporary Intel and AMD CPUs. Measured boot. This is what allows UEFI secure boot to operate. Each stage in the boot process gets hashed, measured. That's with the algorithm that we saw in the previous slide into a PCR within the TPM. The PCRs are checked by the loader against an expected value or an attestation function. And this, once we've gone through the full boot, is ensuring the integrity of the operating environment. Put another way, this is what's ensuring that no unexpected code is executing on the way up through the boot process. So we've got a clean system state. From this clean system state, we may want to demonstrate that remotely or locally. For remotely, we would call this remote attestation, which is a remote element in the ATM network or in any sort of network of systems. We'd be able to verify that the platform is indeed in a specific state using a challenge response mechanism. The next steps after that may be something like releasing a DRM key to that system once it's verified as clean. Local attestation is really about unlocking secrets on the TPM to the local system, in our case that we've been looking at, the the ATM. And then the secrets, again, only released when the system is in a known good state, again, leveraging the PCR. This would be something like your BitLocker key being released. It's, I'd be remiss if I didn't point out that no technology is infallible. There have been, historically, some attacks demonstrated on TPMs. Most involve physical access, and these can largely be mitigated through proper implementations. I should note there are comparatively few attacks on these, successful attacks, and I've split them into two camps here. The first, requiring some level of physical access or proximity, such as interposers, which we demonstrated, which would be sitting on the bus between the mainboard and the TPM. Again, this would not be a problem if the TPM itself, if you're leveraging a firmware TPM, for instance. Deeply invasive silicon attacks, this would actually be ripping the chip apart and putting probes on it. Not very practical, but interesting from an academic standpoint. And side channel cryptanalysis. So this involves running multiple hundreds or thousands of cryptographic iterations that you could force on a chip, and then measuring differences in timing or power utilization to extract keys. Again, not something that would typically be practical in an ATM environment. Below this, there are some software or protocol attacks. So one was an S3. So this is a deep sleep abuse, which would sort of reset the TPM. This was given a CVE in 2018. It's largely been addressed, and ROCA, not a problem with TPMs themselves. This was actually a cryptographic attack on certain protocol implementations. So no technology is infallible. These are largely able to be mitigated. And when we compare to a system that's not using the TPM at all, it's no contest. Using a TPM is the way to go. The benefits are far outweighing the residual risks that are left in a system. Advice for platform engineers, use your FTPM. This is really the way to go. This completely eliminates the physical attacks on a system, which leaves you with just any software attacks that are, or microcode attacks that are found. The ones that are currently out have been mitigated. Further, utilizing the security positive features offered by the TCG spec, there are some optional features such as authorized sessions, endorsement keys, parameter encryption, and using rolling nonces. If you don't know what these are, not a problem. Check the book or check with your local cryptographer, and they'll be able to tell you these very meaningfully improve the security of a TPM deployment. Of course, just like any security system, employ overlapping and complementary security controls, and consider your deployment perspectives. In the TPM or in the ATM space, we have cameras, we have locks on systems, we have tamper alarms, we have monitoring. All of these make sense and further support the security of the system. Also, a good idea to review the deployment periodically and ensure that there are no advances in best practices or patches that could happen. Again, just good solid bread and butter advice. Conclusions. Well, there's no way to guarantee 100% security. Leveraging a TPM can really meaningfully improve the security posture of a system. It can give you platform integrity checking, tamper detection. You can use it to secure and gate access to sensitive cryptographic parameters. You've got local and remote state verification and the ability to perform verified and secured transactions. This is really where the future is going, is verified systems verifying each other to provide cryptographically secured networks. As with any system, a poor or incomplete integration can erode the efficacy of benefits offered by the TPM. Context matters. Any business critical deployment should have its security considered holistically. Please ensure that your engineers or your vendors are using appropriate features to guard against several of the attacks. Again, FTPMs, probably your first and most impactful step forward with these. Once again, I'm Ian Robertson from NCC Group. Thank you very much.
Ian, Aravinda, thank you both for lots of really interesting insights into what TPM means for the ATM and how it can be used more widely to secure networks. I'm going to start off with a question, possibly to Ian, possibly also for you, Aravinda. Ian, you started off talking about how the sort of the TPM is being used more widely for features like Windows Hello and so forth, and the desire to try and do some of these things with a sort of a relatively low load sort of security wise from the user perspective. Do these open up sort of any particular areas of interest as they relate to the ATM, sort of business matters beyond the pure security side of things?
I think it's sort of interesting. Most people have a notion that the ATM itself is just secure. So I think improving the security in the background so that we can sort of have higher levels of assurance around the integrity of that system, that the networks and transactions are themselves secured, is that level of invisible, almost subliminal security that people already expect. So I would say that sort of from the standpoint of this thing that I'm using is secure, would be where we are today. Moving forward to mutually authenticated, mutually secured networks of systems and transactions is absolutely going to be improving the state of.
Aravinda, anything to add to that?
So Tom, I think your question is whether this has, whether the TPM helps with the customer experience. So I don't think so specifically, because I think the TPM is exactly right for securing the infrastructure of the ATM. And you're right that TPMs are used, for example, with Windows Hello, where a user interacts with the PC. However, in our ATM environment, there are multiple users, millions of them. And of course, the way we recognize those folk is with a card and a PIN. So the TPM doesn't kind of replace the card and a PIN. The card and a PIN is, I think, going to be still very important for a long time to come. There could be biometric ways of recognizing people. But I think the TPM helps to secure that infrastructure that will be used to do those kinds of transactions. So it wouldn't be something that, for example, would replace a card and a PIN.
Okay, makes sense. Moving on, you talked about how, I think, Aravinda, in one of your slides, you showed the kind of the diagram diagrammatic representation of the kind of network with not just the ATM, but also the host, the switch, the core, and so on. From your work with banks, where does the responsibility lie, and also Ian, yours, where does responsibility lie for this element of security? Where should the initiative and the responsibility come for these kind of security enhancements?
So let me start that, Tom. So normally what happens is that when we engage with the bank, there is the bank's IT security folk that take part in the project. And of course, they will have a lot of details about what the bank's policies are and how do you secure it. Sometimes they come from the PC side of things, and then they need to kind of modify that for an ATM because desktop PCs and ATMs are not the same thing. And of course, it is those folk that would normally lead the secure lockdown. Now, one of the really interesting things is that most banks are really not there in terms of securing, what Ian called the platform, right? Where, this word attestation, where each platform that connects to an ATM, today, they don't do a mutual authentication that says, is everything on your system verified? It doesn't do that. So today, you might connect with a VPN or TLS connection. There may be certificates on both sides, but all that does is to say, well, is there a certificate on both sides? It doesn't say, is that certificate sitting on a whole pile of malware? It's not saying that, right? Now, where TPM gets to is to say, not only have I verified the certificate, I also know that everything in that kind of blockchain kind of manner, everything, that whole platform is verified. Over to you, Ian, because I know that this is a big subject for you.
Yeah. I was going to say, just really to underscore what you're saying, it's more meaningful. Your identity check on against a remote system is much more meaningful when you can be sure that the system itself, yourself, is intact. And the code that's going to be used to check that remote system has itself been checked. So we're kind of bootstrapping up the trust in the system, and we're starting grassroots, so up, right? Has each element itself verified itself, and then they can move on to verify each other.
Okay, I get you. So we've got quite a diverse audience here at BankSec 2020. We've got people sort of with pure security remits in our bank audience. We've got people who come just as much from a business perspective. So maybe sort of, again, a question for either of you to answer. What would you say is the first step if you're maybe someone who's ATM focused but more on the business side? And then what about if you're someone inside a bank who has more a sort of a security mandate across different elements of IT security?
So I'll go first, Ian, if you don't mind. I think the first step is, firstly, I think to understand that TPMs and storing the keys securely is a critically important point. You need to have a hardware secure element to store the keys. And of course, there's nothing better than something that you've already paid for, because TPMs are standard inside all PCs anyway. It's not an extra cost. Secondly, I think that book that was in my presentation, it's several hundred pages. It should be the starting point for any conversation inside a bank about how do you secure the network. And then thirdly, once you put that in place, then that needs to go into the specifications you build, the vendors that you speak to, and how you specify that the system is locked down. Over to you, Ian.
Really, yes. And the book itself, even if you're security fluent, there is some different nomenclature that's used by the TCG. So what I would suggest is read the book. If there are bits that feel weird or a little bit inscrutable, don't be afraid to reach out to experts. A reputable vendor should be able to walk you through and translate I guess the TCG language to something a little more close to home if you're sort of again, a bread and butter cryptographer instead of a TPM.